this midpoint approximation depends on whether you can evaluate f at whatever point you want. Maybe you can't, in which case maybe the midpoint approximation is off the table for you. But unfortunately, the midpoint approximation is superior in terms of its accuracy. So the question is, what would you want to do to improve your accuracy, but if you can't, in the case where you can't do actually the midpoint approximation? So that is the question. If we can't use the midpoint approximation, how can we approximate f at the midpoint? Well, one thing you can do is you can use a first order Taylor series expansion. In other words, assume f is a line. And if that's the case, then f, evaluated at this fictional point, x a half, that's equal to, or approximately equal to, I should say, 1/2 f at x0 plus f at x1. So from our previous example, when we wanted to evaluate the integral at points x0, x1, and x2, our two areas, area 1 plus area 2, is now approximately equal to 1/2 f of x0 plus f of x1 times the interval x1 minus x0 plus 1/2 f at x1 plus f at x2 times the interval x2 minus x1. So in other words, instead of having the average be on x, now our average f bar 1, our average is on f. Remember, the midpoint approximation had the average of x, so it would be 1/2 x0 plus x1. In this particular case, where we are approximating the function as a line, the first order Taylor series expansion, we can't evaluate f at this midpoint, but what we can do is we can approximate that evaluation by taking the two average values of f. So we have the first average value of f, f1 bar, and the second average value of f, f2 bar, and those two are multiplied onto their respective intervals to give us the rectangular areas. Now, of course, this actually doesn't turn out to be a rectangular area. So this particular approximation is viewing our little sub-areas as trapezoids instead of rectangles, and it's called the trapezoidal rule, for good reason. So if you think about a trapezoid, you're usually thinking about it like this, as I've drawn it here. And this trapezoid has a base, B, but also on the other side it has another base, which is A, and it has a height, H. So the area of this trapezoid is equal to the average between A and B times the height. Now this average between A and B, we have f of x0 being A, and f of x1 being B, and the height is x1 minus x0, or our delta x. Now you might think, well, wait, why is the height a delta in our horizontal distance? And that's because the trapezoids in this case are turned on their side, and they aren't trapezoids as you're used to seeing them. They're what are known as right trapezoids. So they have a rectangular looking bottom, but their top has a slope. So the height is the difference in the two x points, or our delta x, and A and B are our two function evaluations at the two ends of the interval. And the area of this trapezoid, as I can illustrate it here in the case of our previous example, we have our three f of x's, because we have an x0, an x1, and an x2, and we have our f of x's, then what we have is, if I can draw this area of this trapezoid and connect these two by a line, then the area of this trapezoid is a better approximation to the area under the curve than either the right-hand or the left-hand approximation are. It's not as good of an approximation as what we could have done with the midpoint approximation, but it's still superior to the other two that we have accessible to us. Now also note one more thing. Remember how I initiated this discussion of the trapezoidal rule? I said it is the, what we're going to do is we're going to try to do the midpoint approximation, but since we can't, we are going to do a first-order Taylor series expansion. In other words, approximate f as a line, and that's exactly what we've done here. We've connected the 2 points by a line. And so that's our first trapezoid, and our second trapezoid if I can connect them by a line as well. Then we have our second area under the curve, and it's pretty close, so it's going to be kind of hard to see that the hatching is actually extending to the line instead of to the curve. But in any case, what we have is we have our area 1 and our area 2, and when we add them together, we have a pretty good approximation of the integral. So this trapezoidal rule is it's a better approximation. It's more accurate than either the right-hand or the left-hand rectangle approximation. But it's not as good as the midpoint approximation. In general, our error levels are as follows. So in general, the left-hand approximation and the right-hand approximation are both equally bad. And their error is greater than the trapezoidal rule, which I'll call trap z with a little t, and that error is worse than the midpoint approximation. But the problem with the midpoint approximation is it's not always feasible to do. But wait, remember I said, at least for an increasing function, the left-hand approximation always underestimates the integral, and the right-hand approximation always overestimates the integral. If you have a function that's not strictly increasing, if it's like wiggling about, then the left-hand approximation and the right-hand approximation, depending on which subinterval you're looking at, either underestimates or overestimates, depending on if you have the function increasing or decreasing in that subinterval. But suffice it to say that they're both equally bad, and they're bad in two different ways. So because they're bad in two different ways, what would happen if we did a right-hand approximation and then we did a left-hand approximation and just averaged those two approximations together? Would the ways in which they're bad cancel out? And the answer is yes, they do. So you can actually get a better approximation than either the left-hand or the right-hand just by taking the average of the two. So what happens when we do that? So let's take the 1/2, the left-hand approximation, plus 1/2 the right-hand approximation. And what do we get when we do that? Well, we get that's equal to 1/2 times the sum of f of xi minus 1 times our delta x. The sum goes from I equals 1 to n, plus 1/2 times the sum from I equals 1 to n of f of xi times our delta x. Well, we can rewrite this as one big sum, so that's equal to the sum from I equals 1 to n of 1/2 times f of xi minus 1 plus f of xi times our delta x. And now I'm just going to write my delta x actually expanded out, so xi minus xi minus 1. And so what we have here is we have a nice, a good average between the two. And in fact, what it just turns out is that this is the trapezoidal rule. So you can think of the trapezoidal rule in two different ways. You can think of it as approximating the function as a line on your subinterval and then using the trapezoidal area. Or you can think of it as the average between two kind of semi-bad approximations to the integral to get a better approximation. In either case, you get this is the formula for the trapezoidal rule.